Right, so to continue with carbohydrates for today, we're going to recall what we stopped with last time of making it into a cyclic form. So carbohydrates exist in their linear form and then in a cyclic form. So we're going to see how that cyclic form is made. And then we'll talk about how we combine different cyclic forms together, different monosaccharides together, to make disaccharides and polysaccharides. Okay, so here's where we were last time. We were looking at the linear form of the sugar on the far left there. And we remind you what we were looking at here. This is called the Fischer projection. Right? So it puts the number 1 carbon at the top and then 2 through whatever underneath it. In this case, it's glucose, so it has 6 carbons. And I've colored them here. So the top carbon is red, and then green, and then pink, blue, cyan. And then number 6, which is not chiral, is listed as black carbon. Right, so the important carbons here for what we're going to do are carbons number 1 and the OH on carbon number 5, the cyan. Okay, so I've colored that OH on carbon 5 orange so we can track it. Right, so if you remember, we did this before. We're talking about combining an aldehyde, which is carbon number 1, and an alcohol on carbon number 5. Right, so if you combine an aldehyde with an alcohol, you make a hemiacetal. Right, so I need to rearrange this glucose to make it a little easier to see what we're doing. So I'm going to make this molecule fall over to the right. Okay, so anytime you start with these Fischer projections like this, left and right mean things. Remember, left and right is meaningful here. If these aren't the combination you have of right, left, right, right, then it won't be glucose. So we need to be careful how we fold things and turn things. So when I take this molecule, I'm going to make it fall over to the right. So the top, imagine this is just a person standing here. He falls over to the right. Okay, so at the same time, carbons number 5 would end up on the left-hand side of the molecule if this falls over. So when it falls over, the feet are going to kick up behind it. So that's what's shown here. Let's track the colored carbons to see what I've done. So carbon number 1 here is now fallen over to the right. Here's carbon 2 in green, 3 in pink, 4 in blue. And then 5 and 6 are the kind of the legs and feet of this molecule. They kick up behind it. So now we have number 4 here in blue, 5 in cyan, and 6 is sticking up in black. Importantly, the OH that was on number 5 here is now positioned near carbon number 1 because it's fallen over. And if you can visualize this molecule just tripping and falling to the right, here's what you'll get. And because of that, every OH that was facing to the right here, or everything facing to the right, whether it's an H or an OH, all the things to the right side of this Fischer projection, since it's fallen to the right, are now pointed down. Right? So in every case, everything pointed to the right is either still pointed to the right or pointed down. And everything pointed to the left is now pointed up. Right? So if this molecule were to fall over to the right 90 degrees, then everything to the right would be facing downward, and everything to the left would be facing up. And that's what we mean by this conversion from a Fischer projection into what's going to become a Haworth projection. Right? Because left and right mean things, and that meaning is going to be translated into, instead of left and right, respectively, it'll be up and down. So left becomes up, and right becomes down. All right, so let's follow what happens. So this molecule falls over. Here's carbons 1, 2, 3, 4, 5. Number 6 is not involved as usual because it's not chiral. And number 5 has the last chiral center. Remember, this had 4 chiral centers, numbers 2, 3, 4, and 5. Remind me again why number 1 is not chiral?
It has a hydrogen.
Not because it has a hydrogen.
Double bond?
Because it doesn't have 4 single bonds. Right, so it doesn't mean a double bond as well. It could be a triple bond, but it doesn't have 4 single bonds. Right? It has to have 4 single bonds, and those 4 things must all be different from each other. Right, so just because it has an H is not the only way, or just because it has a double bond is not the only way to accomplish that. So don't limit your definition to that. Right? But number 1 is not chiral. Right? It doesn't have 4 different single things attached. Okay? And of course, number 6 is not chiral for what reason?
It has 2 of the same thing, 2 hydrogens.
Exactly. It has 2 of the same thing. It does have 4 single bonds. It met that qualification, but 2 of them are the same. And for this example, they're hydrogen.
I have a quick question.
Go ahead.
To be chiral, doesn't it have to have tetrahedral?
It does have to be tetrahedral, which is what you get when you have 4 single bonds.
Okay, thank you.
You're absolutely right. Right, so it's fallen over to the right. We have our 6 carbons laid out here, right? So red, green, pink, blue, cyan, and black. The orange oxygen of the OH on carbon number 5 is positioned near the aldehyde now. And we can do what we've done before. We have an aldehyde and an alcohol next to each other. I lined them up for you here. And just like before, you're going to break a bond here between this carbon and oxygen. It's going to have only a single bond that remains, as you see over here. We're going to break the bond here between this O and the H. They'll go to no bond here. As you see, there's no bond between them anymore. And I'll make 2 new bonds, because each of these 4 atoms just lost a bond, a bonding partner, and they're going to need one more. So this carbon, instead of bonding twice to this oxygen, it's going to bond once to it and once to this oxygen. So we'll make a new bond here. That closes our ring. And this hydrogen and this oxygen each need a new bond, so they'll bond to each other. So I've erased 2 lines here and made 2 lines in this direction. Right? You can think of it, if it weren't slanted, as a square. Right? I'm erasing these 2 lines and drawing these 2 new ones. Right? And that's what I end up with here. So once again, was carbon number 1 chiral?
No.
No, because it did not meet the qualifications. They didn't have 4 single bonds to 4 different things. After I complete this formation of a hemiacetal, confirm this is a hemiacetal for me. What makes this carbon a hemiacetal carbon now?
It has an OR bond and an OH bond.
Right, so it has an OR group. There it is, OR. And it has an OH, right? And it still has the H that it started with, right? That made it an aldehyde. That H is still there. It did not get involved. It's just along for the ride. So yes, this is a hemiacetal now. If this H had been something else, like another series of carbons, then it would still be there. Nothing would have changed. We'll see that in a minute when we do fructose. But now it's a hemiacetal. It is carbon number 1, the red carbon, chiral.
Yes.
Yes, all 4 things are different, right? It does have 4 single bonds now, and it is now chiral where it was not before. So I've introduced a new chiral center by doing this, because it has an H, an OH, an OR, and the rest of the carbon chain. So those 4 things are quite different from each other, right? Even though these are both oxygen, we don't just look at the first atom, we look at the whole group, and they're quite different, right? So this is a new chiral center. What does that mean?
Now we have 5 chiral centers.
Well, we had 4 chiral centers before. You're absolutely right. We now have 5 chiral centers. All the colored carbons are chiral now. What else does it mean? That's absolutely right. I agree with your answer. But what else does it mean?
Is it 5 squared now then?
It would
The
be
different.
it would be 2 to the 5th. Remember, we changed the exponent. Right. So there's twice as many options now. You're right in the premise of what you were saying. You just had the numbers backwards. But we do have twice as many options as we had before. So this was glucose because of this arrangement, but this is still glucose. It's just in its ring form. But now, because I've added a new chiral center, there's 2 versions of this glucose. There's the one where this carbon is a left-handed, and there's one where this carbon is a right-handed version. And instead of calling them left and right-handed here, because it's still glucose, we call them alpha or beta. Right? And that determines, it's determined by which way this OH is facing. So in our Haworth projection that we've made, everything that was to the right is now facing down. You notice all these are down. And everything that's facing left is now facing up. So this H, this OH, this H are all now up. Right? So when I do this, and I end up with this H and OH here, I could draw them one of 2 ways, because up and down means something. So I could draw the OH pointed up and the H down, or I could draw the H up and the OH down. Those are different molecules, right? Because this thing can't rotate because it's in a ring. Right? It's got 4 different things attached. It's chiral. These are separate molecules. So when we draw the OH group pointed up, the same direction as number 6 here, we're going to call it beta. Right? And when the OH group is pointed down and the hydrogen pointed up, or whatever else was there, whatever could have been in our group, happens to be hydrogen here, but the OH is pointed down, we're going to call it alpha. right? So down would be like to the right over here. We're going to call that alpha. And up would be like to the left over here. We're going to call it beta. Okay, so beta's up, alpha's down. You got to remember those. Okay, so we've turned the straight chain form of glucose into its ring form, right, or its hemiacetal form, right? Did I add or remove any atoms to this glucose molecule?
No.
No. So what can you tell me about its ring form compared to its straight chain form?
It has the same molecular formula.
It has exactly the same formula. You're right. So they're just different forms of the same molecule. So it should have the same formula, and it is still glucose, right? They're not isomers of one another per se because they're the same molecule, but it is a different form. And if you remember the straight chain form of glucose, what formula did it have, right? Or what generic form do carbohydrates have in general?
Those
CnH2nOn.
Right, so C sub N, H, 2N, twice that many, and then O equal to the number of carbons, N. Will these on the right have that same formula?
Yes.
Yes, I haven't added or removed anything, so they have the same formula. Why did this one have a CnH2n? It seemed like some hydrogens were missing from our normal 2n plus 2. Why was that the case?
Because of the double bond.
Right, our double bond was our site of unsaturation. Is that the only way to have a site of unsaturation?
Also a ring.
And guess what we've made? Well, we've traded in our double bond for a ring. So we still have one site of unsaturation going through this process. So the formula has not changed. And this should affirm to you that a double bond and a ring are both equivalent in terms of site of unsaturation. Right? So you can change one to the other. This is fully reversible. It goes back and forth in solution all the time. Which do you think is preferable? The straight chain or the ring form?
The ring.
Why?
Is it more stable?
Why? I know I sound like a 4-year-old asking why, but give me just finish out
Isn't
your
it
answer.
harder to pull them apart, like their forces, intermolecular forces or something?
Well, it is more stable in the ring form. You're absolutely right. It's not so much pulling things apart, but when you put things in a ring form, all right, these angles are more stabilized, right? So this is trying to be tetrahedral all the time, except for this one, of course. And it's more stabilized in a ring because it's easier to have 2 neighbors on every carbon than to 1, and it maintains that stability. Also, you notice we have a severe lack of aldehydes over here, right? There's no more aldehyde group, right, where there was over here. So aldehyde groups are quite reactive, which makes the molecule less stable. Right? So when you go into the ring form, like it does here, it's less reactive. And if you find glucose in solution, like in honey, for example, about 99% of it's in its ring form, and only 1% exists in the straight chain form. But it goes back and forth all the time. It's fairly easy to do, especially if you heat it up. All right, so is everyone okay with forming the rings? Any questions?
you please like how when we say it falls over, like trip over, and the rings on the right go down and the ones on the left go up. Those in the middle, where did they go? Are they up or down?
What do you mean by in the middle?
In the center of the ring, like you see an OH and 2 H's in there.
Okay, so what I'm saying by left and right here is if you look at the Fisher projection over here. Excuse me. If you look at the Fisher projection on the far left, I'm talking about the H's and the OH's that are sticking off of these central carbons. They're either pointed right or pointed left. Right? So pick any carbon you like. Let's do number 2. It's either pointed right or left. Okay? And then if we look at the ring form when we're done, that same carbon number 2 in green has 2 things sticking off of it. Of course, it's connected to numbers 1 and 3 in the chain, right? We still see that over here, 1 and 3. But now the OH that was pointed to the right and the H pointing to the left are now pointed respectively down and up.
Oh, okay, I see it. Okay, thank you.
I know that the drawing it's a two-dimensional drawing. It's a little hard to see, and that's why these little wedges are here. But remember, this ring it's not exactly flat and planar. We know it adopts a chair conformation, but in every case, whether it's a chair or a boat, or if you imagine it as a flat conformation, then there's a plane that goes through the ring, right? And then things are either pointed above that plane or below it. Does that make sense? And if you have your little model kits, you'll see that. If you make this ring form, and then you kind of turn it on the edge so you can see the rings, things are either pointed up above the plane, like the top hemisphere, or below in the lower hemisphere. Things pointed down, like all these guys, were originally pointed to the right over here. And things pointed up, right, like all of these, were originally on the left in this drawing. That's what that means.
Just to confirm, beta's left, right?
So beta and alpha are indications for this new chiral center, right? It was neither left nor right originally because this carbon was not chiral. So here beta means it's pointed up and alpha means pointed down. It's not necessarily left and right because if you go back to the straight chain form, that chiral center doesn't exist anymore. Right? This H and this double bond are neither left nor right. This is not chiral. So we'll only have alpha and betas in the ring form. And beta will be up and alpha when an OH is pointed down. That OH originally came from this carbonyl, yes. But in the straight chain form, it is not an OH and it is not chiral. So it's neither left nor right. And that's why when you make it into the ring form, there's always two possibilities. Because we're creating a new chiral center, and anytime you add a chiral center to a molecule, we remember you get two options. But of course, once you make this beta glucose in its ring form, it can always go back to the straight chain form, which could always turn back into the alpha form. So you can get alphas and betas interchanging, just not directly. They have to go through the straight chain form to do it. And that happens in solution all the time. Any other questions on this closure of the ring to make a hemiacetal? Because it's going to be important for the rest of the lecture. Okay, so let's look at what we can do with it once it's closed. So here again is our, one more thing I forgot to mention, sorry. On the right here, I know it doesn't say glucose, right? Don't let that confuse you. It says glucopyranose. We put that little pyranose in there just as a way of stating that it's in its ring form. That's all that means. It means it's in a six-membered ring form. That's all pyranose means. I don't care if you remember that or not. You can call this beta glucose, and I would be happy with that. You can call this one alpha glucose, and I'm happy with that. This one you don't call alpha or beta because it's neither. It's not chiral. It's just glucose. Okay, so if you call this one glucose, you call this one beta glucose, and you call this one alpha glucose, I'll be perfectly happy with that. Okay, which is what they've done on the next slide. It's just called alpha glucose. They keep putting this D in there because we're only going to deal with D sugars for the rest of the semester. We can assume they're all going to be D. Right? And remind you what D stood for. It's the direction of the OH on that last chiral center. And all of ours are going to be to the right. Okay? So let's look at our alpha glucose here. So this is in its ring form again. And if you remember the straight chain glucose, the orientations, the one on the previous slide I was just looking at, the 2, 3, and 4, the chiral centers there, either go, 2, 3, 4, and 5 go to the right, left, right, right. Right? Like little marching orders, right, left, right, right. Or all to the right except number 3 carbon, which was to the left. So this is the same thing here, where instead of on number 2 being to the right, it's down. I'm not drawing the H pointed up, but there is one. I'm just not drawing all the hydrogens to leave it out of cluttering the image. On number 3 here, the OH is to the left or up, right? Hydrogen's pointed down. And on number 4, it's pointed right or down. Right? So go back and look at those again. It's right, left, right, right. Same thing here. Down, up, down. Okay? So same thing here. It's down, up, down. Number 5 is still pointed to the right. Right? Even in the ring form, it didn't get turned down because it's now in the ring. So it's still pointed to the right. And number 6 was never chiral, so it's still not chiral. Number 1, however, New chiral center, and since it's pointed down, we remember down means alpha. If this had been pointed up, it would have been beta. Right? But let's see a reaction here. This could have been alpha or beta. The drawing happened to choose alpha. And then we add to our hemiacetal, because this is a hemiacetal, right? An OH and an OR on the same carbon. We're going to add an alcohol. Right? This happens to be methanol, but you can use any alcohol. What happens when you have a hemiacetal and you add yet another alcohol? What do you get?
Acetal?
You get an acetal, right? You don't get the hemi anymore. You get the full acetal. So what happens, just like before when we made this one, this carbon, if you look back, this carbon originally had 2 bonds to the oxygen in the carbonyl, right? Here it is. And we erased one and made it a single bond, and it made a new connection to the alcohol that was reacting. It happened to be part of the same molecule, that's why we got a ring. And in the second time, this carbon is going to lose its other bond to that oxygen, right? And it's going to make a bond to the new alcohol group, right? So this CO is going to be broken. Now that would be free as an OH, right? It won't be connected in here anymore. And this carbon will make a new bond to this oxygen of the alcohol, right? You see the alcohol group is now attached at that. It's a new bond. This is not the same O here. This one should be red, right? They messed that up in the figure. This should be a red oxygen. So color that one red. Okay, that's a mistake in this graphic. Right? I always find these things. So this new bond to this oxygen here, and then this hydrogen is not going to be bonded to it anymore. If you look back, you see that OH loses a bond to its H. We're going to do the same thing here. This O and H are going to break their bond. And this H ends up on this O. And because this O is leaving with 2 H's, that makes water, this O should be black. Right? So this H goes on this O, leaves as water. And this O ends up attached to this carbon. That one should be red. Okay, so I'll probably fix this figure for you and upload a new version. So this is a new bond, right? So now this carbon has what attached to it? An OR and another OR, whatever this blue group might be. Happen to be methyl group, could be longer, but it's 2 ORs attached to the same carbon. This is now an acetal. Right? So what I've made is what's called a glycosidic bond. I've made a bond on the side of a sugar. Glyco means sugar, side literally on the side of the sugar. So I've made an attachment on the side of a sugar, so it's a glycosidic bond. Right? And it's a very specific glycosidic bond because this one happened to be alpha. So it's called an alpha glycosidic bond or an alpha glycoside. Right? And what did I attach? It's a methyl. Right? It happened to come from methanol. The alcohol adds this little piece to it. Right? If it were longer, if it were ethanol, there'd be 2 carbons here. If it were propanol, there'd be 3 carbons here. We still get the same water if there were a black oxygen here, and we still get the same ether group attached, should be a red O, from this alcohol component. Okay, we've done this before. We made hemiacetals and we made acetals, and I told you we would do it exactly the same way again, and all this other stuff attached here did not get involved. It's just along for the ride, right? Just like it was before. All those other things attached did not get involved. We just did it in the context of a sugar. Right? So we formed it into a hemiacetal reacting with itself. Then we add yet another alcohol to form an acetal. And we get water as a byproduct. But instead of using just a plain old alcohol like methanol or ethanol here, how about we use another sugar? Isn't another sugar also an alcohol? It's got many OHs on it. It can serve as the alcohol group. So I can take my glucose again. It happens to be another alpha glucose here. So copied it down below. Right? And I'm adding another glucose molecule. Just happens to be an alcohol. Right? So this one's serving as the hemiacetal component. And this one's happens to be number 1, 2, 3, 4 here, is serving as the alcohol component. Okay? And for some reason they colored this one correctly. Right? This OH is going to leave just like it did before. And it's going to take the H from this big alcohol, right? This other part's just an alcohol, just an OH. So this OH leaves with that H to make water. They colored that one correctly. And this carbon, losing its bond to that O, needs to bond to the other O. Right? So I'm making a new bond over here, just like I did before, from here to here. That's the new bond. They did it correctly here. It's connected from this to the new O, and there it is. Because this one was pointed down, right, alpha, it still remains pointed down. I did not change the chirality at this carbon. It didn't go from alpha to beta or anything else. It stays alpha. Right? So same thing here. It's still pointed down. So instead of drawing this bond straight across, they drew it down, and I'm going to do the same thing. It's pointed downward. Right? They happen to draw in the H here to show you that. That H is still there. It was always here. Right? It was always here. They just drew it in for you to show that the H is up and the O is down. Right? That makes this alpha. It was always alpha. And this is a new glycosidic bond. But instead of connecting this sugar to just some carbon chain, it connected it to another sugar. So I've connected two sugars together. And that would make what from these two monosaccharides?
A disaccharide.
Right. This is how we make our disaccharides. So a disaccharide is nothing special. It's just a way of connecting one sugar after it's in its ring form to another alcohol. And the alcohol happens to be serving, or the sugar, second sugar, serving as the alcohol. They're usually also in their ring forms, but you notice that carbon did not get involved. It wasn't involved at all. Right? It was one of its other carbons, OHs, serving as the alcohol. So I know this one's the hemiacetal. How do I know it's this carbon's the hemiacetal and not this one?
He has OR and OH.
Right. Same rule we keep applying. It has an OH and an OR. I know that's the only carbon in this whole thing that has two O's on it. Right. So I know that's the hemiacetal carbon. This one doesn't have that, so it's just an alcohol. Right. So I connect those two. I get a new glycosidic bond. It happens to stay alpha. If it started alpha, it'll stay alpha. This one, whether it was alpha or beta, was irrelevant because it's going to remain whatever it was. And even in that case, this one can still open into its straight chain form. Right? Because nothing's stopping this one from opening back up. This one can no longer open because there's no OH left here. I can't make a carbonyl anymore because there's no H to remove off of this oxygen. There was when it was in this form, but once I close it into a acetal here and make the disaccharide, this carbon cannot open anymore. Right? I can't open this ring. This one's fused shut. This one, however, is free to open and close all at once. So whether this one was alpha or beta was irrelevant, and it's still irrelevant because it can open and change to the other form if it wants to. Right? But this one being alpha remained alpha. If it happened to be up, it would have remained up and stays closed in that form. Okay, so once we get to the full acetal and we make that carbon into no longer having an OH, it's got two ORs, it is fused shut and it can't open anymore. The other one is still a hemiacetal, so it's free to open and close all at once. Right, both of these two reactions, they're identical reactions, just using different alcohols. What type of reactions are they? And I give you a hint in red.
Dehydration synthesis.
They're dehydration reactions. Another name for it is a condensation reaction, where you're condensing two things together at the expense of losing a water molecule. So if you want to call it dehydration synthesis, that's perfectly valid. Just call it dehydration. Or if you want to call it condensation, that's also an appropriate name for this. Right? So let's talk about disaccharides, and that's what we'll spend the rest of the time on today. You know how they're made now. So we started out with a monosaccharide that exists in both its linear and cyclic forms. Right? It goes back and forth all the time. It prefers the ring form because it's more stable. Right? So in the linear form, it's either going to be an aldehyde or a ketone, and we called those aldoses and ketoses, the sugars. In the ring form, they're either going to be a hemiacetal or a hemiketals, the old name if it was a ketone, but we grouped those in with hemiacetals modernly. And then that hemiacetal, as you remember, has an OH and an OR on the same carbon as this guy does down here. It's glucose again. Right? In its ring form, is this an alpha or a beta glucose? This picture here.
It's alpha.
It's alpha because the OH on the hemiacetal carbon, OR-OH, you know it's the one, points down, not up. Okay? And this glucose, let's confirm it's glucose and not some other sugar. So it's on number 2 should be right, left, right. So it's down, up, down. So that's definitely glucose. Right? It's not some other sugar like galactose, which we'll see in a minute. And then the other sugar here is also glucose. It didn't matter if the second sugar here is alpha or beta because it's not going to get involved there. The OH for the glucose on number 1, 2, 3, 4 here is always down. Otherwise it wouldn't be glucose. So it didn't matter if this one was alpha or beta. And that's where a lot of people make mistakes in doing this, and they assume both of them must be the same, and that's not true. Right, so the first one here is alpha, guaranteed. It's pointed down, because if it's not alpha, it won't make the sugar we're about to talk about. And the second sugar, glucose here, doesn't matter if it's alpha or beta. I'm only interested in the OH on number 4. We'll do the exact same reaction we did on the previous page. We're going to lose the water molecule, and this again has a mistake. Can somebody spot the mistake in this figure? It's the exact same mistake from the previous one.
The OH is supposed to be taken from the first glucose.
Yeah, so the blue shading should be around this OH, not this O, but it should be this OH and just this hydrogen. And the O that's left over is actually the one from the second sugar right here, because you know this one leaves as water. So again, fix those colorings, and I'll probably fix this one later. I'll find a better version of this picture. But the water molecule comes from the OH on the first one and the H from the second sugar. Right? But again, we get this glycosidic bond. It's an alpha glycosidic bond because this one's pointed down. This one was always pointed down because number 4 of glucose is down. That's not what made it alpha. This is what made it alpha. Okay? And if you look at this in a more realistic way, instead of these sugars in this drawing sitting side by side, they're actually in their chair conformations, as shown over here on the right. So here's one, number 1, 2, 3, 4, 5, and then 6 sticking off the ring. And then the other one's the same way, 1, 2, 3, 4, 5, 6 sticking off the ring. And number 1 we said was alpha pointed down. It's fairly obvious in this drawing that the OH was down, right? This is also down for number 2. Number 3 is pointed up. I know it looks like it's going to the side, but remember these exist, maybe you went over this in your lab course, they exist in the axial and equatorial planes, right? So this is axial versus equatorial. Right? So this one does have one pointed down axially, but it's also got one pointed up. It just happens to be equatorial, so it's pointed kind of outward instead of straight up. Right? And number 4 again is equatorial, pointed outward instead of up. Right? The same thing over here. So clearly this one was down. This one's also still down. Right? It's not pointed up. Right? So you get it. It's kind of hard to see this one. It's not quite slanted as much as I would like it to be. But you get the idea. They're both still down. And this makes the sugar we call maltose. Right, it's the first disaccharide we're going to look at. It's made of 2 glucose molecules. Right? The first one must be in its alpha ring form, and the second one doesn't matter if it's alpha or beta. Right? And I put them together. I make this alpha glycosidic bond, and I call it an alpha 1,4 glycosidic bond. I'll see what those numbers mean. When I say alpha 1,4, I mean the 1 is the carbon from the first sugar that's involved, and the 4 is the carbon from the second sugar. Actually, they're O's from those carbons. So the first one, number 1's oxygen, yes. So number 4 of the second sugar is oxygen, yes. And the first one had to be alpha, guaranteed. The second one is neither alpha nor beta because this is not the new chiral center. Number 4 is what it is for this sugar. For glucose, it happens to be down. If it were galactose, it would happen to be up. But it's an alpha 1,4 because number 1 is the new chiral center that I made when I created the ring form. Number 4 never changed when I went from straight chain to ring. It was always pointed down or to the right for glucose. So don't call the second one alpha or beta. It's not. Number 1 is alpha, and number 4 is number 4. Okay, so let's look at this one more time. Here's the same picture. I actually got the colors right on this one when I found it. So we have alpha glucose on the left plus a glucose. And it doesn't matter if this one's alpha or beta. Number 1 is not getting involved. And so we do this combination again. This one has all the H's drawn for you, but they're kind of cluttering up the image. You could not draw them if you didn't want to. But number 1's OH is down. That's what made it alpha. And number 2 was down, 3 was up, 4 was down. That's what made it glucose. And in the second one, it's also glucose. We get number 2 down, number 3 up, number 4 down. This one happens to also be alpha, but it was irrelevant. I could have put the OH on top and it'd be beta, like this one, and it wouldn't have made any difference. Because when I'm making maltose, only the first one matters. They both must be glucose, but only the first one has to be alpha. So first one being alpha, second one, number 4, is always down for glucose. This is the correct color combination for the water leaving. Right? There's an O left behind in between, and I drew it this way so that they're both still shown as the alpha and down here. And this makes maltose, like we've seen before. Right? So what if my starting material, instead of being alpha glucose, is actually a beta glucose? So that's shown on the bottom of this figure. So we're going to start with a glucose here. It's still glucose. Confirm that. Number 2 is down, 3 is up, 4 is down. So down, up, down, still glucose. And number 1's new chiral center OH is pointed up, not down. So this is beta. Right? The second one, again, this one on the right doesn't matter. So I erased that part of this figure where it listed them as alpha or beta. This is beta as well, but it doesn't matter. I could substitute an alpha here and it would make the same product. So this one must be beta. And again, the color scheme's right. I'll lose this OH, the H from the alcohol, to make water. And this time, since this one is pointed up, I drew the figure a little differently to indicate this one is still up. And this one, number 4, is obviously still down. So it's still beta. By pointing up, this is beta. Number 4 is always down for glucose. So these are both made from the same starting materials, pure glucose. It's just this one happened to be in its alpha form when it formed this, and this one in its beta form when you made this. And the enzymes that do this in plants and animals are very specific about which ones they select. So the enzyme that makes maltose will not select a beta glucose for this position. This one, it doesn't care because it's not checking this in. It only checks that it's glucose. So it has to be an alpha glucose plus some other glucose. And this one, the enzyme that makes Cellulose in plants, must select a beta glucose followed by just any old glucose. Right? And that's how you make Cellulose. These two are quite different from each other. They behave quite differently. You are able to digest maltose. If you were to ingest this as food, you have an enzyme that can break this bond. Right? But the same enzyme, called maltase, that breaks this bond, cannot cut cellulose. It can't reach this bond physically. So you can't digest cellulose. This is why you can't eat wood, but you can eat other things that contain maltose, like malt sugars, right, or glycogen or something like that, which we'll talk about in a second. Right? But you can't digest cellulose or cellulose.
I have a question.
Uh-huh.
The difference between it, the top and the bottom one, the maltose and the cellulose, is just that it's alpha and beta?
That's exactly right. They're both
Okay.
disaccharides. They're both made from glucose and only glucose. But when you make them, the maltose, the first sugar of it, the first glucose, must have been alpha. The second was irrelevant because it's not involved over here. And for cellulose, the first glucose must have been in the beta conformation. Again, the second doesn't matter. And when you make these two, again, this second sugar can open and close all at once. So if it was alpha, it can become beta. Beta can become alpha. The second one can open and close all day. But the first one, now that it's no OH here anymore, 2 ORs, it's an acetal, is fused shut and it can't change. So that's why these are different molecules. Okay, so let's look at these two. Here's maltose. Once again, I threw it on here in a different version of it. This one happens to be alpha on the right. It could change to beta anytime it likes. It can open and close again. But this one is fused shut. So we call it an alpha 1,4. You notice number 1 over here is not involved. This number 4. So alpha 1 is bonded to number 4 of the second sugar. So the alpha tells me number 1 must be alpha, and number 4 is just number 4. Right? Realistically, it doesn't look like this if you put it in its chair conformation. And it looks more like this. And because of the way this is arranged, you get this angular structure to the maltose. Whereas if this were a beta bond, as you see down here, then it looks like this. Right? And this actually more accurately describes it. This one must be an alpha glucose, and this one could be alpha or beta. It doesn't make any difference. This one is a beta glucose, and this one doesn't matter if it's alpha or beta. Right? They're missing some hydrogens here on these oxygens. So this one has a more straight chain appearance, right? It's not a straight chain, there are rings, but you see it's more linearized, it kind of lines up with itself. And this one has a kink in this arrangement. So if I were to take many of these and put them together, right? So if I put an alpha glucose next to another alpha glucose, next to another alpha glucose, next to another, I'm going to get a really long chain of these, right? And it's not going to be called maltose anymore. It's going to be called not cellulose, but starch or amylose or dextrine. Right, so all these ones put together, glucose, 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 they're all alpha. You notice they're all pointed down here with their little linkages. Right? In this case, they all need to be alpha because one is serving as the first sugar of the next pairing. Right? The very last one could be either one, of course, but all these others need to be alpha to make starch or amylose or glycogen. Those are all the same names or different words for the same thing. We generally call it starch if it comes from plants. We call it glycogen if it comes from animals. But it's the same exact molecules. They only differ in how they branch, and we'll talk about that much later in our last block for this course. But if you make cellulose from cellobiose, all of them are going to be in their beta arrangement. So instead of pointing down, they all point up, down, up, down, up, down, right? So this is very misleading that they look like they're both pointing up, but it's more like this, where this one's up and that one's still down. And if you put these in long chains, our amylase or maltase or any of these enzymes we use to cut this is able to cut these bonds, but unable to reach these bonds, right? So these little pliers here representing the enzyme can degrade starch or glycogen or amylase or amylose, but you cannot degrade cellulose. This is why you can't eat wood. What organisms are able to digest this? And I always get the wrong answer here, but go ahead and say it anyway. What organisms can eat cellulose or wood?
Fungi.
That's the right answer. That's good. Any other organisms?
Termites?
Almost. People always say termites, but it's not actually the termite who's doing it. The termite has a collection of bacteria in its gut that's able to digest the cellulose. Right? The termite.
Is it prokaryotes or?
Yes, the prokaryotes, the bacteria that live in the termite's gut, actually can digest the cellulose for it. Right? So the way that you kill termites, and a lot of these chemicals that kill termites don't actually kill the termite, is they're antibiotics. They kill the bacteria in their gut. And then it would have the effect like if you tried to eat wood, you'd be unable to digest the wood, and it would kill you by blocking up your digestive system. So the same thing there. If you kill the bacteria in their gut with antibiotics, then the termite will continue to eat wood because that's what it eats, but it can't digest it and it dies. Right? So the termite itself doesn't digest the wood, the bacteria do. And that's how we know that antibiotics work to limit or kill termites. And of course fungi can do this too. That's how you get dead trees that fall in a forest get degraded, mostly by the fungi that degrade them over time. Right, good. Right, so let's look at a couple disaccharides that are not the same as those. Those were made of pure glucose, right? One more review. They were made of pure glucose. So alpha glucose plus a glucose makes maltose and an alpha 1,4 bond. A beta glucose plus a glucose makes cellobiose and a beta 1,4 bond. Okay, so what if we don't start with glucose? Let's start with a different molecule. Let's start with galactose. Right? It's a cousin of glucose. What's the only difference between glucose and galactose?
Galactose is a beta glucose because the OH is on the top.
No, the alpha and beta have nothing to do with it because you can also have alpha galactoses. Just ignoring, imagine them into straight chains. What's the only difference?
Like what is it? One on the left and one was on the right or something?
That's
Or on different sides?
yes.
Good question.
You're close. Which one?
The third one?
The third OH. Yes, that's true, but it's on the carbon number 4.
Okay.
So if you look back at glucose, and I'll get to your question in just a second. If you look back at glucose here, we had 1, 2, 3, 4, 5, 6 carbons. This was glucose because it was right, left, right, right. If I switch number 4, remember that from last time, that's the only difference you had to remember for galactose, then it would be right, left, left, right. Okay? And in its ring form, what would be the difference for glucose here to galactose? Galactose, this OH would be on the top and this H would be on the bottom because that's number 1, 2, 3, 4. So you switch these around and you see that in my picture here. Instead of having glucose where the number 2 is down, number 3 is up, and number 4 is down, it's down, up, up. This is galactose. Okay, question? Someone had another question? No? Okay, so the only difference between glucose and galactose is the arrangement of the OH at number 4. Okay, so number 1 doesn't matter because this can open and close into a straight chain form. Right? So it could be up or down for glucose or galactose. But number 2 is to the right or down. Number 3 is up or to the left. And number 4 for glucose was down, but in galactose it's up. That is the only difference between glucose and galactose. Right? Number 4's OH is up rather than down on glucose. Okay? So instead of starting with a glucose here, we're going to start with a galactose. And it happens to be a beta galactose because an alpha won't work for this sugar. So it's galactose because I know this. I know it's galactose because number 4's OH is up, right? And I know it's beta because the OH on number 1 is up in its ring form. That doesn't make it galactose. That makes it beta, right? The fact that number 4's OH is up makes it galactose. So this is a beta galactose. And then I have a plain old glucose over here, right? It doesn't matter if this is alpha or beta because it's not going to get involved. And again, number 4 is always down for glucose. So it must be a beta galactose and it must be a glucose. It doesn't matter if it's alpha or beta. Again, not getting involved in that second sugar, right? And once again, we're going to connect these two. What's going to leave here is water. We get some options. Tell me which of these OHs, the top left or the bottom right, which of these O's leaves as water? So is it top left OH or is it the bottom right OH?
Top left.
Yes, the top left. So this is the hemiacetal carbon that's involved, and this is just an alcohol involved. Right? This one is not involved. Right? So the first sugars, the hemiacetal, and why do I need to call it beta? Because that's the one involved. I need to know where the OH is. The second sugar could be alpha or beta. It's irrelevant because it's not involved. I need to know this one, and it's always down for glucose. So this OH here is going to leave with which H? Which H leaves with it? It's going to make water.
H on the glucose, and it's gonna make water.
Which H on the glucose?
The OH group.
This one, right?
Yes.
Yes, the H that's on the OH. Not this one at all. This one's not involved. It sits there, it never moves. It's there when we're done. Just like this one's not involved. It stays there when we're done. So it's this OH and this hydrogen leave as water, and that leaves this carbon needing another bond, and it leaves this oxygen needing another bond, so they'll bond together to make the new glycosidic bond right there. Right? Just like we've done before. The only difference between maltose and lactose is that I started with a galactose instead of a glucose here. Right? Or sorry, maltose, not maltose, but the cellobiose, because this one's up. Right? So the only difference between lactose and cellobiose is that I started with galactose instead of glucose. This one's still beta, much like our cellobiose was, right? Except we started with glucose there. So can you digest lactose? Since it's beta, right? It's a beta 1,4 linkage, much like this guy was. Can we digest lactose?
Yes and no.
Excellent answer. Tell me why.
Yes, some people can, but no, some people can't because they don't produce lactase.
That's right. So the reasoning behind it, I know it's kind of a trick question, right? It's kind of an unfair because your brain's wanting to give two different answers. One, because it mimics cellobiose in this beta 1,4 linkage, you're thinking, hey, that enzyme can't reach it. We should not be able to digest that. And you're right that amylase cannot digest it. This enzyme, the one that normally cuts the alpha 1,4 bonds, cannot digest lactose. I agree. We do have an enzyme called lactase that can digest that bond. Now, that's a key hallmark of mammals, right? One of the key hallmarks of mammals is we have mammary glands. It gives us our name, and they produce milk or lactose as a food for our offspring. And it's great because non-mammals can't digest it, so it's kind of a selective food for our mammal species. So when we ingest lactose as an infant, we make a lactase, right, that digests this bond, and you're able to break it up into galactose and glucose and use those sugars for fuel. But as you get older, in nearly every mammal on the planet, as you want to wean the child off of breast milk, right, because the child's going to start, or the new animal, the baby animal, right, not necessarily a child, but the new growing animal is going to eventually wean off of the mother's milk and onto their own foods. How do you talk them into doing that? Right? Well, you make them unable to digest the lactose. And after a few sessions of not being able to digest your food, you're going to stop wanting that food. Right? You're going to go on to eat your own foods. So adult mammals generally cannot digest lactose because they stop making the lactase enzyme, like you said. In humans, we've adapted to ingesting lactose as adults. Right? It's a mutation where we no longer get rid of that enzyme as an adult, and we're able to continually ingest lactose for food. And it's not because we continually breastfeeding our entire lives. That's silly. It's because we've adapted to having domesticated animals, other mammals that produce milk, like sheep and goats and cows, right, that also produce milk, and that was a staple of the diet to get through the winter in those cold Arctic winters, right, from the last ice age. And if those who didn't have that mutation didn't survive that process, and so it was selected for. So this was done in the Scandinavian region of Northern Europe, the Vikings and those that were descendants from them. And so those who are lactose tolerant were all mutants, right? So if you're a member of that crowd, put your hand up. I can't see it, so it's okay. Right? So if you're a member of that, you're a mutant like me that can digest lactose as an adult, and we were descendant from that selected for mutation. If you're lactose intolerant, congratulations, you're normal, right? You're not a mutant. You don't think of yourself as unusual. You're normal, like the rest of the mammals on the planet. That's what you're supposed to do, right? And this mutation has also come from other areas in the world, right? Many places that you'd use domesticated animals to ingest their milk. This mutation has arisen many times, not just in Northern Europe. But if you look at areas that don't have a lot of domesticated animals for food, where their main staple is rice or wheat or some other plant, the incidence of lactose intolerance, or the more likely that you're normal, is higher. That's what that means. Okay? So if you want to know more about that, we can always talk about it after class too. Right, so here's another sugar, one you're more familiar with, called sucrose. Right, this is our typical table sugar, right, really sweet sugar. And it's made from two sugars again. It's a disaccharide. It's made from alpha glucose, much like maltose was. Let's confirm this is glucose. So looking at number 2, we have down, up, down. That's definitely glucose. And it's down at number 1, so that's alpha. And then the second sugar is actually a fructose. Now, we haven't talked about fructose yet. So fructose is a cousin of glucose again, but remember it was a ketone sugar, right? A ketose. So here the carbonyl wasn't on number 1, it was on number 2. And I'm going to leave this as an exercise for you to do. Imagine taking the straight chain fructose, look back at our last slide set, and turn it into its ring form. Make it fall over to the right and do that attacking. But number 1 is not going to be involved because it was not the carbonyl carbon. Number 2 is right here, right? This is number 1, this is number 2, and it fell over to the right. So number 1, 2, 3, 4, 5, 6 is still sticking off the ring. Okay, not involved. So it made a smaller ring. Instead of a 6-membered ring, we made a 5-membered ring because carbon number 1 was not involved. And when you do that, number 1, 2, 3, 4, 5's O, same one that was here, number 5's O, number 5's OH, right, is the same one that makes the new bond. Here's our new bond for making the ring. Right, so if you go through that on your own, the same way we did glucose, you make the ring form of fructose. And when you do so, you're going to see that this new carbon, number 2, that wasn't chiral before, is chiral now. It's got an OH. There's no hydrogen on it. Instead of a hydrogen, like glucose had, it's got carbon number 1 attached. Right? But OH, carbon number 1, the OR here, and then the other carbons, they're all different. So this is, again, a new chiral center. And that's going to happen every time you do one of these ring forms. Right? So this could have been beta or alpha. How do I know this one is beta?
The OH is at the top.
The OH is pointed up. Yeah, the OH is pointed up, just like number 6 was. Right? So number 2's OH in this case, because number 1 is still not chiral. Now, number 2 wasn't chiral, and it is now. Right? So this originally had 3 chiral centers, and now it's got 4, whereas this one had 4 and has 5 now. So this one is pointed up, so it's definitely beta. If this one had been pointed down, we'd write the OH down here, and carbon number 1, the CH2OH, would have been written up here. Okay? But to make sucrose, this one's unique. Sorry, go ahead.
I have a question.
Go ahead.
Can you explain how that one's number 2 again?
When you look at fructose in its straight chain form, the carbonyl group is on carbon number 2. It's a ketose, not an aldose. So because it's on number 2, that's where we're going to make the new chiral center. Right? Number 1 is not involved, just like number 6 was not involved. Right? It's sticking off at this point. We don't always go to carbon number 1. We always make this new attachment at the aldehyde or the ketone or the carbonyl group. Remember how we did that back here? Right? We had the attachment at the carbonyl. If this were fructose, this carbonyl would be on number 2, not number 1. So this attack would have been on number 2, not number 1. So number 1 would not have been involved. They would have attacked at number 2. Right? So here we're looking at fructose in its ring form. Number 1 is not involved. So number 2 is the new chiral center. It's up, so it's beta. And here, just like with maltose, we needed an alpha glucose. So glucose is number 1 was down. And unlike the other sugars, in this case, the 2 chiral carbons are going to interact. Right? You notice in every other case, we had the new chiral center of the first sugar with some other carbon of the molecule, not the new chiral center of here. It's always number 4 of the other one. Here, the 2 chiral centers are getting involved. Number 1 from glucose, and because number 1 is not chiral, it's number 2 of fructose. These 2 are getting involved, right? And I drew it this way not to confuse you. Sometimes they turn this one around and put them side by side, which is kind of confusing. But I drew them on top of each other to make it easier to see. Right, so this one's pointed down, and this one's pointed up. These are the 2 OHs that are going to get involved. And water is going to be relieved as a product. Where does the water come from? It's clearly from one of these OHs. Which one will leave as water?
One from glucose.
Right, again, just like before, the one from the glucose, the first sugar, this OH will leave as water with the H from where? Where's the other H coming from?
The hydroxy group on fructose.
Right, the number one, what carbon number? Because they all have one.
On number 2.
On number 2, right, this one. So this H goes with this OH to make the water. This O is left behind to make a bond to this carbon. So they look like really long bonds here, but they're not really that much longer. I just drew it this way. So you can see that this carbon number 1, the new chiral center for glucose, alpha, because it was down, and the new chiral center for fructose, number 2, because it was a ketose, it's pointed up because it was beta, right? And these 2 are interacting with each other to make this new glycosidic bond. So what did I call these before? I called them beta 1,4s or alpha 1,4s because that involved the 2 things. Here I'm going to call it alpha beta 1,2 because the alpha describes number 1, right here, pointed down, and the beta describes number 2 pointed up. So this is called an alpha beta 1,2. It doesn't mean 3 things are attached. It's an alpha with respect to number 1 and beta with respect to number 2, and that's my new linkage. How is sucrose?
Question.
Okay, go ahead.
How are you knowing which one is 1? Like how to label which one is number 1?
Number 1 is the first carbon of the chain, right? And I know from aldehyde sugars, it's the hemiacetal carbon because they were aldehydes, right? So this is the one with 2 O's on it. I know it's number 1. The one here with 2 oxygens is not at the end of the chain, right? So this must have been a ketose sugar, so it's on number 2. Here's number 1.
Okay, thank you.
How do I know this side's not number 1? Because then if I did that, the one with 2 oxygens on it would have a much larger number, and I know that's not the case. It's either an aldehyde or a ketone on number 2. So I know which ones are number 1 or 2. Okay, so my question is, how is sucrose different from all these other ones we've talked about? How is it different from maltose or cellulobiose or lactose?
Oh, it has a ketone sugar?
It has a ketone sugar. I agree with that answer. It has a fructose and the others don't. I agree with that answer. Both are not wrong answers. I'm looking for a different answer though.
Is it a smaller ring?
It does have a 5-membered ring because it was a ketose, but that's along the lines of those first 2 answers. Not a wrong answer again, I agree. But not the one I'm trying to get you to say.
Isn't it how the O is bonded on the right side?
Wait, say that again?
How the O is bonded on the right side?
I'm not sure what you mean by bonded on the right side.
Never mind.
I just drew these on top of each other instead of side by side. That might be what you're trying to say. That doesn't make any difference. These bonds can rotate. This can flop all over the place.
Okay, never mind.
So what's different about it? It has something to do with the second sugar. And it's not that it's a ketone or that it's a fructose or it's a 5-membered ring or anything like that. What's different about how it was connected?
there is no OH on the end, like on the left or the right, to connect to another one?
That's true. So this thing is not going to make a long chain. It's kind of truncated, right? There's no OH or no other hemiacetal or hemiketal group that can continue a chain. That's along the lines of my answer. And that means what? In all the others, let's look back at one, like lactose, for instance. When I put these together, this other chiral center on the right, this new one I made, it didn't matter if it was alpha or beta, right? We've said that quite a few times because this can open and close all at once, right? So it can be beta sometimes, it can open and become alpha, but this one was fused shut, right? What about on sucrose?
Are they both fused shut?
They are both fused shut because the two new chiral centers that would allow them to open again are the ones involved. Right? So that's indicated in the name. You notice both of them had to have indications of their chirality. And so this one is fused shut permanently. So sucrose cannot open and close anymore. There's a consequence to that we talked about last time. Right? And this will help you out when you do that lab for your lab course. In all the others, if I were to react lactose or maltose or cellobiose or any of these other sugars we talked about except sucrose with a reducing agent, right, or an oxidizing agent, would they be able to react? In other words, is there an aldehyde available to react? Like a Tollens test or a Benedict's test?
No, they cannot react.
Why not?
Because there is no other group for it to react with because it's shut on both sides.
Well, this, I'm talking about for lactose here, or cellobiose or maltose. This other one can still open. Right? Even though this one is fused shut, the second sugar is still able to form a straight chain. It opens and closes all the time. So in some cases it will be open, right? And it will react with your Tollens agent or your Benedict's agent, and you will get the reaction. You'll see the silver mirror or the conversion from the blue to the brick red solution. Right? But in the case of sucrose, you will not, because it cannot open to a straight chain anymore. There is no available aldehyde or ketone on this thing, right? And no way you can convert to an aldehyde because both are fused shut. So in this case, sucrose is considered not a reducing sugar. All the other monosaccharides we mentioned are reducing sugars, even the ketones, and you'll get that answer in lab about why they are. But in this case, the cellobiose and the maltose and the lactose are still considered reducing sugars because they can react, right? They can be oxidized. But sucrose cannot. Both are fused shut. And that's what makes sucrose such a great sugar for heating and cooking, right? If you heat up any of those other sugars, right, the chance of it forming the aldehyde form goes up, right? The straight chain form goes up. So any of those others, if you heat them up, right, like put them on the stove and you put milk in a pan and heat it up, that sugar for lactose will open and close more often, right? The glucose on the right will open and close more often. And that could cause oxidation of the sugar, right? But sucrose, as much as you want to heat it until you completely, denature and burn the thing, will not open and oxidize, which makes it a great sugar for making hard candies and pies and other things like that. But if you tried that with milk sugars like lactose, they don't come out so well if you heat them too hot. Right? So that's why sucrose you can do this with, and sugar substitutes you cannot do this with. So try doing this with our artificial sweeteners. You can't heat them up that well; they fall apart. Right? So that's one of the reasons why sucrose will be a better sugar for cooking than glucose or lactose or any of those others. Take honey, for example. It's mostly glucose. And if you heat it up, glucose has that second one that can open and close, the second sugar if it's disaccharide form. And then when you try to cool the honey back down, it's most likely going to crystallize. Right? It'll form a solid instead of staying fluid because you now mixed up the forms in which it exists. Whereas sucrose, no matter how many times you heat and cool it, it only exists in one form, like you see it. Right? Another one I want to talk about is chitin. Right? So this is much like our cellulose, right? It's just like cellulose or cellobiose, and I'm putting it into a long polymer. So it's made of glucose entirely. So these are all glucose molecules, but I've modified the glucose. So confirm that this is glucose with me, right? So here's number 1, because it's got 2 O's on it, right? This is number 2. It should be down, and it is down, but it's not an OH for some reason. So it would be an OH down, because there's the H pointed up. Number 3 is pointed up, number 4 is pointed down, number 5 still in the ring, and number 6 is still not chiral. So this was a glucose at one point, and it was connected to the next one, and the next one, and the next one, and they flipped every one over to keep showing you that it's a beta type bond. So this is connected just like cellobiose and into a polymer, just like cellulose. Right? But the difference is I've modified that OH on number 2. Right? So the OH on number 2 is no longer an OH at all. It's actually a nitrogen now. Right? So instead of being an oxygen, it's a nitrogen. And on the nitrogen, I've put another 2-carbon group called an acetate group. You don't have to remember that. I'm just showing this as an example. Right? So we can modify sugars. And this is called glucosamine now, right? With this nitrogen here instead of an oxygen. It's called glucosamine instead of glucose because I've added an amino group. And on the amino group, I've added an acetate, an N-acetyl group. So it's called N-acetylglucosamine. Right? And it's many copies of N-acetylglucosamine back to back to back. And that's what makes this molecule called chitin. Right? And chitin is what makes up the shells of these crustaceans. Right? And in insects as well. So it makes a hard shell if you make this polymer of this sugar. Right? And so instead of using this as a backbone, plants don't put this group on here, right? They just have regular old cellulose as their backbone for making the plant's cell walls and cell membranes stiff. Right? And then the one you're familiar with, or you will be familiar with, is heparin. Right? It's a manufactured polymer of sugars. So here we're going to take a molecule and put it in a long chain again. And the length of the chain varies. So we make some that are several dozen sugars long, and some that are 100 sugars long, and some that are somewhere in between. And heparin is a combination of all those different lengths of polymer. And it's the activating molecule for the enzyme antithrombin 3, or the enzyme inhibitor antithrombin 3. So when you add heparin, or give heparin to a patient, it activates this antithrombin 3 molecule, and it inhibits the enzyme thrombin, which is needed for making a blood clot. So overall, what will heparin do? Right? They call it a blood thinner. It doesn't thin anything out. It's not like paint thinner. It's kind of a misnomer. It actually prevents clotting. That's what heparin does. So it doesn't thin the blood at all. It just prevents the clotting effects in the blood. And so if you give someone heparin, this is what you're giving them, this molecule at the bottom. They're all alpha 1,4 linkages. This is a terrible drawing for this reason because it looks like there's a carbon here, right? It shows this little angled thing here. That's a terrible idea. It actually should be drawn down to the O and then back up to the other carbon. That's a better way to draw that. Don't draw these little angles because it's misleading you thinking there's a carbon there. There is not. Right? But it's again made of what sugar? What sugar is this originally? So if we look at it, number 2 was down. It's been modified. It was an OH. Now it's got a sulfate on it. Number 3 is up. Number 4 is down.
Glucose.
It's glucose. So I've modified number 2 with a sulfate, and I've modified number 6 to a carboxylic acid, which we'll cover next time. Right, so I've oxidized it all the way to a carboxylic acid. And on the other copy of the sugar here, it's also a glucose. I've modified the number 6 with a sulfate and modified number 2 with this nitrogen and a sulfate. So quite a bit of modifications to this heparin molecule. And it alternates this one and then this one, this one and then this one in this long chain. And because of this sugar, the way it folds up, it activates this molecule which inhibits clotting. And the last thing I want to talk about is undoing this process. How do we undo this formation of a disaccharide? Okay, so if we start with a disaccharide at the top here, let's figure out which disaccharide this might be. See if you can figure it out with me. Let's decide that it is a disaccharide. You should see 2 sugars there. They're connected. What kind of connection is this?
Glycosidic.
It is a glycosidic bond. I'm looking for the number and letter prefixes for it.
Alpha.
Alpha 1,4.
It's an alpha 1,4, right? So this is the number 1 of this sugar, and number 4 of this sugar are definitely involved, and number 1 of this sugar is alpha. It's pointed down. So this is an alpha 1,4 bond. What sugar is this?
Maltose.
the sugar on the left, of the two sugars involved, what monosaccharide is this?
It's glucose.
Glucose, because it's down, up, down. And this one on the right?
It's also glucose.
Also glucose, because it's down, up, down. And like he just said, putting those two together, glucose plus glucose, and its alpha linkage, alpha 1,4, makes maltose. Right? So maltose, if I add water to it, and of course I have to add an enzyme to help this process proceed, will be broken apart into its two constituent components. And again, they got the colors right here. I don't know why they couldn't on the original one. Same authors. And so this water molecule breaks this bond right here, the one we just made, right? And it comes apart. The H from the water goes on this one to make the alcohol, and the OH ends up on this carbon to make this OH group here. So I've gone from an acetal, adding water, this is hydrolysis of an acetal, in the context of sugars, so we call it hydrolysis of a disaccharide, into the hemiacetal and alcohol. You've done this before. We did this 2 lectures ago. I'm just doing it in the context of sugars now, to show you that this chemical procedure happens all the time. This is how we break down sugars into monosaccharides. Right? If this were a longer chain, not just 2 of these put together, but many, many thousands of these put together, this would be a polymer of glucose known as glycogen or amylose. Right? And if you add the water and the enzymes, they would all get broken down into regular glucose. Right? It's how we degrade molecules of glucose from their storage forms or as food.